So yes, this is where we're going to really get to the nuts and bolts of enzymes and the bulk of a lot of what your paper has to do. You can already talk about and should have a good concept of the different types of structural information that your paper requires, but not necessarily the enzyme mechanism and like inhibition and things like that. So hopefully in the next handful of classes, you'll be able to pick up on those terms and be able to be more well-versed in it for your paper for the second draft as well. This chapter and chapters 8/9 are the ones that I go into the most detail. Now, usually in a normal semester, I take the most time in doing it because there's just a lot of material, and you really, unless you take enzymology or like chemistry of cancer or something like that later on, you don't really get to cover it in any additional fashion beyond this class. Okay, just some generic terminology here, and to get used to the vernacular, which I apologize that I can't change the color scheme, but that the colors are about the same, at least on mine. I will change this one because that looks just identical. Looks like the German flag. Okay, so an enzyme is just a fancy word for a biological catalyst. The vast majority of enzymes are proteins, except for, and true, because my background is in enzymology, and so true enzymologists hate the fact that they like to, that some books, like your own textbooks, call self-splicing RNAs an enzyme, because technically they aren't. Because if you remember, if you go back to Gen Chem, what's the definition of a catalyst? Right, it itself does not change, and it speeds up a chemical reaction. It is true, these self-splicing RNAs, they speed up the reaction, but they change themselves. They work on themselves, and so they cut themselves out of, the introns and things like that, and for alternative splicing. So technically, they're only a pseudo enzyme because they are their own substrate. However, I just throw that in there just because of the fact that it is a slight misnomer. If we were doing an enzymology class, we would go into greater detail. However, there are ribonuclear protein complexes that are true enzymes. Okay, for example, the ribosome, the part that does the chemistry behind the reaction to make proteins, is actually RNA. The protein parts of the ribosome help hold things together, but they don't do the chemistry. And ribonuclease P, which is my background, it has a catalytic RNA component, and it's the RNA that does all the work. The protein actually just helps it get rid of the product, and so that way it has a preference for substrate over products. Because you have to realize, if you think back to Gen Chem, this is going way back, like Gen Chem, if you had your substrate or your reactant and your products, and this is what it looks like normally for the curve, then what happens is whenever you have an enzyme, all it does is it lowers that activation energy, so it increases the likelihood of going forward or backwards by the same amount. And so that's why sometimes you have these other cofactors that help it to go more one direction versus the other. Enzymes actually increase the rate of reaction up to 10 to the power 20-fold. Okay? So it makes it much more feasible on a biological time scale, and especially in vivo. Okay? Just because a reaction, it doesn't, notice in this example that I used before, it doesn't change how much substrate or reactant you start off with or the amount of product made. So thermodynamically, it's the same. If something was spontaneous before, it's still spontaneous. It's just that instead of taking a gazillion, that's the scientific term, maybe a billion years for it to work, it takes, a matter of a couple minutes or something like that. That's why it speeds it up so greatly. But it doesn't change the actual equilibrium concept of how much products versus substrates would be made or not made. Many enzymes are enantiospecific, to where they will catalyze only one stereoisomer, or maybe they preferentially catalyze one stereoisomer over another. Then there are some that actually can catalyze multiple reactions. And the term, which I usually get some snickers for that, is an enzyme that has multiple substrates or catalyze multiple reactions. It's called a promiscuous enzyme. So if they talk about something being promiscuous or promiscuity, it means that it has multiple substrates, or it can do multiple reactions. It's promiscuous. It gets around in the enzyme world.
You said it has multiple substrates,
or does different types of reactions. I mean, it's the same thing. But so, for example, she's not here today, but I know not to give it away, but the enzyme that Jessica is doing for hers is one of the aminotransferases. The aminotransferases in general, they do 3 different types of reactions. They do the aminotransferase reaction, they do a racemase reaction where it can change between the D and the L version of the amino acid, and they do decarboxylation reactions. So they're very promiscuous. Whereas the DNA polymerase, typically DNA polymerases they have a high degree of fidelity. They are not very promiscuous. They only take certain nucleic acids, and they will only make another DNA. And they don't make mistakes. They don't have a high error rate, which is good for us, right? Because otherwise we could get cancer. Okay, and so, or they could put in the wrong thing, and that just wouldn't make sense. And so that's why they have high degrees of fidelity. Whereas other enzymes, you want them to be more promiscuous because they have multiple jobs. And just as I was referring to this little energy diagram here, the rate of the reaction depends on its activation energy. I'm going to bring this up that way. I don't know whether that's going to be coming along. Oh. So the rate of the reaction depends upon its overall activation energy for that transition state. Okay. But the enzyme just provides a different alternative, like a different pathway. So this is actually I'm just going to put one in here, a blank one. This is what it kind of looks like. Oh, sorry, there's something on my... So we have our reaction diagram. Sometimes they call it the reaction coordinate. This is our energy. And this would be, we have our substrates, or in Gen Chem they call them reactants. And it goes to make products. Okay? So on this end, we'd have enzyme plus the substrate. We get your enzyme back, right, because it's unchanged, plus the product. And so if it was uncatalyzed, it's in that black color. What happens here is you still start off with the same substrate, but it lowers that activation energy. You're always going to get at least one hump or one little minima. Sometimes, depending on the pathway, you may even get more. And it goes and it makes the exact same product. So that's why. But now we can see here the activation energy at this point is much smaller than the original activation energy right there. So that's the reason why the reaction rate increases. And please note, once again, whoops. Oh, I did not mean to do that. It's going to increase, this is what's called the forward reaction, by the same amount that it increases the backwards reaction, because it decreases the overall hump by the same amount. Okay, so it has no effect on how much substrate or product you're going to get overall. If you had a gazillion years, you'd still end up with the same ratio. It just makes it much more feasible on a biological time scale. And you're going to see more of these figures as we go along. I just wanted to explain that out in that little blurb. Another term is called a cofactor. There are cofactors, and there's something called coenzymes. Okay, which many times, many times you use them interchangeably, but there are slight nuances. Typically, a cofactor is usually something that's really small. Many times, it may be something that's inorganic, like metal ions or something like that, whereas a coenzyme is usually another little protein or another something that has no activity by itself, but that whenever it comes together in the quaternary interaction, it makes the enzyme active. Okay. But like I said, even many times will use cofactor and coenzyme interchangeably. with the exception of almost everybody will say a metal ion can be an example of a cofactor. But all it means is that it's an additional component that's required for the enzyme to be completely active. Mm-hmm. Wait a minute, did I have this on here like multiple times? I think I do. Okay. And so we've already talked about an example. You can even have cofactors that are not in enzymes. So for example, the iron that has to be in heme in order for hemoglobin to bind oxygen, that would be a cofactor. So these are some of the really important biological inorganic cofactors. So these are usually metals, but they don't have to necessarily be a metal. Selenium is not a metal, but usually they are metals. Many of these, you've either talked about in the past or you've probably heard about in biology classes and things like that. But copper, and this is just an example of the enzyme that utilizes it. But copper enzymes are used in a lot of redox reactions for the transfer of electrons. Same goes for the iron, and that's because both of these can change their oxidation states. Copper is copper 1 or copper 2. Iron, in theory, can be iron 1, 2, or 3. The ones that are biologically relevant are iron 2 and 3. Potassium and magnesium are utilized many times. In fact, this one, you had those Miss America questions, like world peace. Okay, just like in enzymology, it's enzymatic, it's energetically favorable, or it's entropically favorable. That's like an answer. But whenever you just have to guess a cofactor, if you know that there was a cofactor there, and it should be, and there's any type of phosphate, like ATP, CTP, any of those, or if it's just a phosphate nearby, magnesium is a good guess, because 99.9999% of the time, you're going to have magnesium anytime there are phosphates, or even carboxylates, for that matter, around, because they're negatively charged, the magnesium is positively charged. That's usually, especially next semester. Sometimes you get stumped, and I know there's a cofactor. If you see a phosphate anywhere nearby, you just it's magnesium. Manganese is also important. Manganese is a heavy metal, but you do have to have trace amounts of it. There are certain enzymes, and we talk about some of these next semester. Molybdenum, we do talk about dinitrogenase, is for nitrogen fixation, or nitrogen metabolism, I should say. And so molybdenum is required, nickel is required, selenium, zinc. We've already talked about carbonic anhydrase. And zinc, many times, not always, but many times what it's used for are for structural reasons. It helps coordinate, because unlike many metals, which unfortunately I don't think you got to cover this whenever you took Gen Chem, because as I mentioned, I think a time or two before, you probably didn't get to cover the coordination chemistry chapters, but a lot of the transition metals, they can have more than one shape when they coordinate to things. Some of them will be tetrahedral, some of them can be trigonal planar, some of them can be octahedral, where it kind of looks like a big sphere. Zinc is not one of those. Zinc is always tetrahedral, and so it actually helps for structure. Zinc can also help act as a Lewis base, and help activate water molecules to become even better nucleophiles. Oh, see, this is where the coenzyme, technically, versus a cofactor, is usually something that's much more complex organic molecule or a small protein. Sometimes they call them protein cofactors, or like your vitamins that you take many times. Those are technically coenzymes versus a cofactor, which is something that's really small and usually inorganic. But like I said, many times I use it interchangeably, and almost everybody does without thinking. So some of these examples include, it kind of got cut off, but I think you can see them. And I've got another picture of it coming up. And you can also look either in your book or on the PowerPoints that I've posted on MyFire. But I like this one because it shows you the coenzyme. It gives you the type of reaction that it's involved in. You're going to need to know this table and the one that follows it. I mean, they're similar. They show the same type of things. And then these are the precursor. Okay. And so, for example, coenzyme A, which you hear a lot about, next semester, it's used all the time. In fact, a lot of times it's even abbreviated CoAsh. Or if you see acetyl-CoA, it just means it's been acetylated. Okay? And it's used to move acyl groups. And so pantothenic acid, there are other compounds, but pantothenic acid is your big one. And so that's one of the reasons why if you look at your multivitamin sometimes, it'll list that big pantothenic acid on there. It's because it's used to make coenzyme A in vivo in your body. We have the cobalamin, this deoxyadenylyl cobalamin. A lot of times they just call it cobalamin. It's coenzyme B12. It comes from B12. And it's used to move hydrogen atoms. We're not talking about protons now. We're talking about hydrogen atoms and alkyl groups. And so if you think back to organic chemistry, remember how difficult it was to add like a methyl group? Remember, a lot of times if you wanted to add a methyl group, does anyone remember what's the rule of thumb to add methane, CH4, which is completely inert? What did you have to do? Does anyone remember what's the first step to make it active before you could add it to anything? Yeah, but you can't just remove a hydrogen. How did we have to remove that hydrogen? Free radical halogenation. We can't have free radicals in our body. Well, I mean, they do naturally occur, but you don't want free radicals in your body because it could do lots of things. So we couldn't do free radical halogenation and then use that in a substitution reaction. So we instead, one of the main way that we do it is with cobalamin, with vitamin B12, because it can actually move methyl groups. It uses methionine to do it, but it uses that to remove methyl groups and even to move other alkyl groups or hydrogens without it being a free radical. Okay. Then we have, this didn't show up very well, but it's flavin. So flavin adenine dinucleotide, which the way that that's abbreviated is this. Flavin adenine dinucleotide, and whenever it has its hydrogen on it, it's called FADH2. It's used in redox reactions. Okay. It's related, I'm going to skip down, it's related to nicotinamide adenine dinucleotide, which it's fine with me if you just remember that it's NAD plus. Whoops, it's FAD plus. NADH. Oh, wait a minute, there's not a plus on that one. Oh, that thing's so big. It's FADH2. And sometimes the NAD is phosphorylated, and then it's called NADP plus or NADPH, but the only difference is that there's a phosphate group on it. It, too, is very similar. The nicotinamide, whoops, let me switch back. Nicotinamide and the flavins do the same type of reactions. What they do redox reactions. Okay. So this is vitamin B2 riboflavin, and that's niacin. You see niacin written down. In between that, there's lipoate or lipoic acid. It's just when it's lost its hydrogen, it's lipoate. And that one's also involved. It's involved in two different types of reactions. We'll talk a little bit about it next semester. Actually, we talk a lot about it. It's usually in huge complexes that also have like FADH2 in it and maybe NADH, and they're just major complexes that do that. Pyridoxal phosphate, some of you may have already had that. I know at least one person has pyridoxal phosphate in their enzyme because they came in to ask me. They met me in office hours to ask what it was. And it comes from vitamin B6. And it's involved in the transfer of amino groups. Tetrahydrofolate, which comes from folic acid or folate. Remember, if it just lost its hydrogen, it's called folate. It's very important. It's also involved in moving methyl groups. And every woman, even remotely of childbearing years, should make sure that she takes a vitamin that has folic acid. Because studies have shown, even years in advance, that folic acid deficiency or folate deficiencies can ultimately result in neural tube birth defects. And so that's why it should make sure, and typically men don't have as many problems with it, but make sure that you get plenty of folate. And then we have, this is TPP, thiamine pyrophosphate, and it moves aldehydes, and it comes from vitamin B1, which is thiamine. This is the same thing. I don't know why it got shifted so high. But you can see it's the coenzyme, the type of reaction, and then the vitamin precursor once again. So you can see this is just the same thing. It's just a little bit, it's just worded a little bit differently, but it's the exact same principle here. I think it works. Okay. Don't be surprised if something like this comes up on future quizzes or exams. And definitely next semester we talk about all the time. We'll say we'll be doing a reaction for acyl transfer. So this is, for example, in your breakdown or building, either breakdown or building of your fats. Those are big acyl groups. And so it's going to take coenzyme A, which once again was CoAsh. Any type of acetylation, which is also used, for example, in regulation of replication and access to DNA, which, whether the histones get acetylated and deacetylated, that has to do also with coenzyme A. And so you're going to see it over and over and over again. Or if I asked you, name something involved in one carbon transfer, then we're talking about tetrahydrofolic acid in particular. Biotin does do it, but usually it's carboxyl groups.
Would you like to know, like, the vitamin precursors?
For some of them, I want you to know the vitamin precursors. It just makes sense. Some of them, folic acid is tetrahydrofolate. Or, some of them. But it's also good to know, especially if you're going to medicine, that you know what your B vitamins are, that kind of thing. So there we go. All right. Then there's some other terms, which I've already hinted at. There's holoenzyme. What a holoenzyme means is it has everything it's required for catalysis. Everything is there. If it has a coenzyme or a cofactor, if it has to come together in a big quaternary structure, then and that's what I mean by the subunits. So everything is together, catalysis can occur. Then it's called the holoenzyme. If it's missing something, like if it's lacking its coenzyme or its cofactor, it's called APO. APO, if you think back to, medical terminology, means without. So it means it's without something. And then we've already talked about a prosthetic group, which is usually a coenzyme or cofactor that it's almost always covalently attached, like the heme. However, there are times when it's bound so extremely tight and the KD is so low that you just can't ever get it off. Once it's added on, it's hard to get it off, and so they call it a prosthetic device, or not a prosthetic device, prosthetic group, but it's similar or akin to a prosthetic device, in humans. Okay, I want you to know these. There are only 6. So there's actually a group. That's like if you think back to organic chemistry, there's the IUPAC, which comes up with the official names for the elements and for how to name organic compounds. There's one for enzymes. It's called the Enzyme Commission. And you may have even been reading on your enzyme paper, and all of a sudden it'll give you your name, and in parentheses it'll say EC, 4.12.32.624, whatever, or something like that. That's its Enzyme Commission, its EC number. Because it literally would tell you if it was, what did I say, a 4? If it was a 4, it means, it's a type of lyase. And of course, then it talks about the different families. It's like its own taxonomy system. I don't care about that you memorize the numbers. I want you to know their names and what they do. Some of these are really obvious. A transferase means it's going to transfer a functional group. So that's why aminotransferases is a specific type of transferase that transfers amino groups. Methyltransferases will transfer methyl groups. Oxidoreductases do redox reactions. That's the same thing as saying transfer of electrons. Okay? Oxidoreductase, redox. You're going to find out that there are some that have common names that you just have to memorize later on. Like dehydrogenase specifically is an oxidoreductase that uses NAD or FAD. Kinases, which that's one I always have you memorize next semester. Kinases are literally a type of transferase, but that transfers phosphate groups, but it has to come from ATP or CTP. I'm sorry, ATP or GTP. It can also be CTP. Those are the two biggies. Whereas if it's a phosphorylase, that's a transferase where it uses and transfers phosphate groups that don't use ATP or GTP. Which is why if you learn your family names, it helps you. It helps so much. Hydrolases do hydrolysis reactions. Now remember, sometimes they're named for their backwards. And so a hydrolysis reaction, you would think, oh, that means you're adding water to it, you're hydrolyzing, you're moisturizing. But sometimes the one that's important in vivo is where you're breaking it down and it's a condensation reaction. That still technically would be a hydrolase. Lyases, I have to say, are probably the most, at least for me, was the one that I would always forget. And it was the hardest one to explain. So lyases, usually, what we're talking about is their addition or removal of groups between double bonds. I guess in theory triple bonds, but you don't really see that in vivo. Double bonds. But sometimes the lyase, like that double bond is only intermediate. And so you may not see it in the beginning or the end. And so, but technically it has a lyase function because it added, it took a group away to make a double bond and added a group to a different carbon to make it single bond again. And so that would be a lyase. Isomerases are really easy. It just means it goes from one isomer to another. These also have another common name called a mutase. Technically, isomerase is the formal name for but there are some like phosphoglucomutase. Literally means it takes one glucophosphate isomer and turns it into another glucose phosphate isomer. And then we have ligases, which you probably have heard the term ligase already. In what class have you heard them talk about ligase? Pardon? I couldn't hear you. I'm sorry. Yeah, biology and genetics and everything, because ligases literally, well, of course, I was definitely old school before they had all the computer games and stuff. Like, we had to, take, pieces of DNA that were little pieces of paper, and we had to, cut them with the restriction internuclease, and then use the Scotch tape to tape it back together to put your gene together. That was a ligase. So ligases, what they do is they form single bonds, essentially, carbon, 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 sulfur, carbon, oxygen, carbon, nitrogen, by condensation reactions that utilizes ATP or some other type of high energy intermediate. And so that's why, technically, that's the reason why even polymerases would be a type of a ligase. Overall, it's just a very specific type because you're making a new single bond between two nucleotides. So that's what a ligase does, right? It glues it back. For example, an RNA ligase glues two pieces of RNA together. Okay, I'm going to go ahead and I will... No, don't do that. I'll go ahead and I will